and B's power increases by 1. B to the 0th power, B to the 1st power, B to the 2nd power, B to the 3rd power, and B to the 4th power. A plus B to the 5th power. A starts off at the power that the binomial is being raised to, the 5th power. B starts off at the 0th power. Then the next term, A's power is decreased by 1, but B's power is increased by 1. The next term, A's power is decreased by 1 down to A to the 3rd, and B's power is increased by 1 to B to the 2nd. Then A's power is decreased by 1 down to A to the 2nd. B's power is increased by 1. Hold on a second here. Let me take a look at something. Yeah, A's power is decreased by 1, and B's power is increased by 1. And then A's power is decreased by 1 down to the A to the 1st power, and B's power is increased by 1 to B to the 4th. Then finally, A's power goes down to A to the 0th power, and B's power increases to the 5th power here. So do we see these patterns here that are evident when you raise these binomials to various powers? Now, the only other thing that is interesting is where do these these coefficients come from? Like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Where do those exponents come from? Well, ladies and gentlemen, the exponents, we can show where the exponents come from by a wonderful construction known as Pascal's triangle. And this is in honor of a mathematician by the name of Blaise Pascal, who contributed not only to the math field, but also to the sciences. Okay, Pascal's triangle. And the triangle is very easy to construct. It starts with a 1, there's 2 1s here, 1, 2, 1, 1, 3, 3, 1. Now, how am I getting these here? This 2 came from adding this 1 and 1 together. This 3 came from adding this 1 and 2 together. This 3 came from adding 2 and 1 together. 1. Now what's 1 plus 3? That gives you 4. 3 plus 3, 6. 3 plus 4, 3 plus 1, 4. And then it ends with a 1 out here. Next row of Pascal's triangle. 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and then 1. All right, and you can continue going on down to any row of this triangle here. Now, what's the significance of these numbers, and how do they relate to the binomial expansions up here? Well, this row right here gives us the coefficients of the expansion of a binomial raised to the 2nd power. 1, 2, 1. 2nd power. 1, 2, 1. See that? This row gives you the coefficients of raising a binomial to the 3rd power. 1, 3, 3, 1. 1, 3, 3, 1. This row gives you the coefficients of the expansion of a binomial to the 4th power. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Finally, this row down here gives you the coefficients of raising a binomial to the 5th power. 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. And on this goes. So what an amazing triangle, because it does give you the coefficients of a binomial expansion to any power. Notice this triangle is also extremely symmetric. For instance, to the left of 2, you have a 1. To the right of 2, you have a 1. Okay. Here you have 1, 3, 3, 1. Perfect symmetry here. To the left of 6, you have 4 and 1. To the right, you have 4 and 1. Here you have 2 10s, and to the left of the 2 10s, you have a 5 and 1. To the right, you have 5 and 1. So you have perfect symmetry with this Pascal's triangle there. Any questions about all these observations here on these binomial expansions so far? Any questions here? All right, so here's what I want you to do, ladies and gentlemen. I'm going to give you your first classwork. I'm going to have you take a plus b and raise it to the seventh power. Now that means you're going to have to take Pascal's triangle down. How many more rows am I going to have to take this down to raise a plus b to the seventh power? Anybody?
Two more.
Two more. I'm going to take it down one more row for you guys. 1 plus 5 gives you 6. So 1. Notice we always start with a 1. We always end with a 1. So 1, 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And then we have a 1. These would be the coefficients of raising a binomial to the sixth power. Now, here's what I want you to do for classwork number 1. I want you to raise a plus b to the seventh power. So you're going to have to go down one more row with Pascal's triangle to basically indicate or find out what the coefficients have to be. But just remember what happens to a and b again, ladies and gentlemen. A always starts out with the power of the binomial, and then its power decreases by 1. The second term starts out at the 0th power, and then its power increases by 1. Okay, so see if you can, using the patterns that are obvious here, and also by establishing this last row of Pascal's triangle, see if you can write the expansion of a plus b to the seventh power. Now, if you want to do this the long way, a plus b times itself 7 times, we're going to be here for a long time. So that's not the way to do the problem. I want you to use Pascal's triangle, the bottom row, and also all the observed facts as to the powers of the first and last terms, how they vary term to term to term. You guys go ahead and do that. We'll check your result. Okay. A plus b to the seventh power. Okay, so in order to do this expansion, a plus b to the seventh power, first of all, it'd be nice to know what the coefficients are. And the coefficients can be found by completing this row, the bottom row here of Pascal's triangle. So here we go. 1 plus 6 is 7. 6 plus 5 is 20. 15 is 21. 15 plus 20 is going to be 35. 20 plus 15 is 35. 15 plus 6 is 21. 6 plus 1 is 7. And then you got a 1 out here. This row of Pascal's triangle will give you the coefficients of raising a binomial to the seventh power. So here we go with the expansion now. The first term of the binomial always starts out at the power the binomial is being raised to, and the leading coefficient is going to be positive 1. So 1a to the 7th, technically times b to the 0th power, plus the next coefficient is going to be 7. 7 times a's power decreases by 1 down to the 6th power, b's power increases by 1 to the 1st power, plus the next coefficient is 21. A's power decreases down to the 5th power, b's power increases to the 2nd power, plus 35 is the next coefficient, times a to the 4th power times b to the 3rd power, plus the next coefficient is 35, plus 35 times a to the 3rd power, b to the 4th power, plus the next coefficient is 21. 21 times a to the 2nd power times b to the 5th power, plus 7 times a to the 1st power times b to the 6th power, plus your last term is 1 for the leading coefficient, a to the 0th power, b to the 7th power. Cleaning up this expansion here, b to the 0th power is 1, so this is really a to the 7th, plus 7a to the 6th, b to the 1st, plus 21a to the 5th, b squared, plus 35a to the 4th, b cubed, plus 35a cubed, b to the 4th, plus 21a squared, b to the 5th, plus 7a, b to the 6th, and a to the 0th power is 1, so this is plus 1b to the 7th at the end. Notice the sum of the exponents is always equal to the power the binomial is raised to. 7, 7th power. 6 plus 1, 7th power. 5 plus 2, 7th power. 4 plus 3, 7th power. 3 plus 4, 7. 3 plus 2 plus 5, 7. 6 plus 1, 7, and 7th power. Did anybody get that expansion?
Yeah.
Is this making any sense here? You got to admit, this is long, but could you imagine trying to multiply this out by itself 7 times? You want to see long, you go ahead and do that. That'll take you forever. You got to admit, this is a much more powerful way of doing that, a binomial expansion to that large power. Okay. Now, ladies and gentlemen, you could, continue this Pascal's triangle down to any level. Okay. Obviously, the further you keep going on down, the triangle becomes wider and wider and wider, all right, as we keep adding more and more coefficients, more and more terms. But, there's also an easier way to generate these numbers of Pascal's triangle. Instead of, going down row by row by row by row, which is not really that bad of a deal, but still, it does start to become cumbersome. And you know how these numbers come into existence in Pascal's triangle? Wait a minute, somebody said, can you explain how you know where the exponents go where? Okay. When you're raising a binomial to a power, the first term always is raised to the power the binomial is raised to. So a to the 7th power. The second term always starts off at the 0th power, b to the 0th power. Then each term you go further to the right, the first term's power decreases by 1. The second term's power increases by 1. You see what's going on here? Okay. So that's how you know what exponents you're going to have. All righty. Does that answer your question? Okay. All right, so that's all there is to the exponents. It always works that way. Now, these numbers of Pascal's triangle can be generated by using our combination function, which we looked at in section 8.7. Recall, combination is a number, is a way of enumerating possible arrangements when we select R things from N things where order does not matter. So our combination function, believe it or not, generates these numbers of Pascal's triangle. And that I want to show you that next. Okay. In other words, Pascal's triangle can be generated by using your combination. So you can have 0 in combination with 0. You can have 1 in combination with 0, and then 1 in combination with 1. 2 in combination with 0, 2 in combination with 1, and 2 in combination with 2, 3 in combination with 0, 3 in combination with 1, 3 in combination with 2, and 3 in combination with 3. So this is the sum of these two previous terms. This is the sum of these two, okay? 4 in combination with 0, 4 in combination with 1 is the sum of these two. 4 in combination with 2 is the sum of these two. 4 in combination with 3 is the sum of these two. And finally, 4 in combination with 4. So it's the combination function that generates the terms or the numbers in Pascal's triangle. You can continue to go onwards here. Notice there's a distinct pattern here. R always starts at 0 and then ends with a value equal to what n is. Okay, so R starts at 0 and ends at 4. R starts at 0 and ends at 3. R starts at 0 and ends at 2. R starts at 0 and ends with 1. Okay. So you can see there's a unique pattern here. So the next one would be 5 in combination with 0. 5 in combination with 1 is the sum of these two. 5 in combination with 2, sum of these two. 5 in combination with 3 is the sum of these two. 5 in combination with 4 is the sum of these two. And finally, at the end, 5 in combination with 5. All right. So let's try this out. This last row here, which gives you the coefficients of raising the binomial to the 5th power. I want you to get on your calculator and I want you to find all these combinations. Go ahead and find all your combinations. Remember how we do that? So for instance, 5 in combination with 0. You get on your calculator, you hit 5, you hit your math button. You got to go over to probability. You go down and grab the NCR function and you type in 0 and then enter. So go ahead and crank out all these combinations on your calculator for this last row and convince yourself that you do indeed get the numbers of, this should be 1, this should be 5, 10, 10, 5, and 1. Make sure that you convince yourself that those combinations generate those values, which we've seen on a previous slide. Okay. So that's where those numbers in Pascal's triangle come from. They come from combinations. Now, another thing is keep in mind that notationally speaking, N choose R could also be represented this way. All right, some textbooks use this notation to represent the combination function. In either case, this represents N factorial divided by R factorial times N minus R factorial. All right. And the combination along with the permutation function is illustrated in section 8.7, of which I did put a video on Canvas for your viewing. If you missed the class where I did go over the combination and permutation, you definitely want to watch that video on 8.7. And you definitely want to watch it anyways, because it also goes over probability rules that I did not have enough time to do during class. So make sure you do watch that video 8.7. That is on Canvas. All right. Are we getting these numbers here when we crank out these combinations on our calculator? Okay, make sure we are generating these numbers here. All right. So another way to symbolically represent Pascal's triangle, and I'm going to use this notation here. This is 0 in combination with 0, 1 in combination with 0, 1 choose 1, 2 choose 0, 2 choose 1, 2 choose 2, 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4, etc., etc. So some textbooks make use of the parenthesis notation as opposed to the C notation. All right, so I'm just cluing you in here. Means the same thing. All right. All right, any question about where these numbers of Pascal's triangle are coming from? They really are generated by the combination function. And because, ladies and gentlemen, they are generated by the combination function, we can be a little bit more compact in how we express a binomial expansion. And that compact portrayal of binomial expansions is embodied in what's called the binomial theorem. Okay? So I'm now going to lay out officially the binomial theorem, of which this section is really all about. So here is the official binomial theorem in all of its glory. And all theorems in mathematics do have a proof, and so this being a theorem has no exception. This is not a proof writing class, though. If you're interested in seeing the proof of this theorem, I can probably dredge it up for you. But if you stay in this math business long enough, eventually you'll start learning how to write proofs of theorems. And that normally comes usually at your junior level of mathematics at a university. If you're majoring in mathematics, you start writing proofs usually the third year in your math career. Okay. All right, here we go. Let n be a positive integer. All theorems have their requirements, their assumptions, if you will. Then the expression a plus b to the nth power is given by a plus b to the nth power. Here is the binomial theorem. It's given by n choose 0 times a to the nth plus n choose 1 times a to the n minus 1 power b to the first power plus n choose 2 times a to the n minus 2 power times b to the second power plus dot 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 plus n choose n minus 1 times a to the first power b to the n minus 1 power plus finally your last term is n choose n times a to the 0th power b to the nth power. This is the binomial theorem, which basically generalizes the expansion of a binomial. And notice the coefficients of each term are indeed generated by the aforementioned combinations rather than taking your Pascal's triangle down to an appropriate row. You can just use combinations to generate the coefficients. So you don't need Pascal's triangle anymore. Pretty neat. Another observation, notice the sum of the exponents of each term always add up to equal the power the binomial is being raised to, and nth power. N minus 1 plus 1, n minus 1 plus 1 adds up to n, nth power. N minus 2 plus 2 adds up to n, nth power. n plus n minus 1, excuse me, 1 times n minus 1, or 1 plus n minus 1, that's what I meant to say, adds up to n. And 0 plus n is n, okay? Notice on your combinations, n is always, well, the top term or the first term of your combination is always equal to the power the binomial is being raised to. The bottom term represents our r. R always starts off at 0, then increments by 1 until it terminates at the power of the binomial. So you can see with all these distinctive patterns here, very obvious patterns, it's not difficult, ladies and gentlemen, to do a binomial expansion once you just, realize all these patterns that are evident. It's really not that difficult of a thing to generate a binomial expansion. And it's a lot easier to do than if you were to grab the bull by the horns and try to multiply a binomial by itself a large number of times, which is not only tedious and time consuming, but also the chance of creating an error is greatly increased. Okay. All right, any questions about the binomial theorem? Okay, let's try another expansion now. So we will try to take 2x plus 3 and raise this to the fourth power. So the instructions will say expand. And like I said, the long way of doing this is multiplying this by itself 4 times, and that's not the intention. The intention is to make use of the binomial theorem. Okay. All right, so here we go. So my first coefficient is going to be 4, choose 0, times my first term, which is 2x raised to the power of the binomial, times the second term raised to the 0th power, plus the second term has a coefficient, which is 4, choose 1. The first term's power decreases by 1, so 2x is raised to the third power, and the second term's power increases by 1 times 3 to the first. The coefficient of the third term is going to be 4, choose 2, times the first term's power decreased by 1 down to the second power, and the second term's power increased by 1 to the second power. Plus, the next term is 4, choose 3, that would be its coefficient, times the first term's power decreased down to the first power, times the second term's power increased to the third power. Plus, here's your last term. 4, choose 4 is the coefficient. First term's power is decreased down to the 0th power. The second term's power is increased to the 4th power. And essentially, that's your expansion, ladies and gentlemen. You just have to, actually clean this up and simplify this now. Now, what is 4 to the 0th power? Well, you can just get on your calculator and you can dial that up. So 4 to the 0th power is going to be 1. And this is 2x to the 4th power times 1. This is 2x to the 4th power. 4, choose 1 is going to be 4 times 2x cubed times 3. 4, choose 2 is going to be 6 times 2x squared times 3 squared. 4, choose 3 is 4 times 2x to the first power times 3 cubed. 4, choose 4 is 1 times 2x to the 0th power is 1 times 3 to the 4th power. Okay. Further expansion, here we go. What's 2x to the 4th power? 2 to the 4th power is 16. This is going to be 16x to the 4th. 2 cubed is 8. And 8 times 4 is 32. And 32 times 3 is 96. It's going to be 96x cubed. 2 squared is 4. 4 times 9 is 36. And 36 times 6 is going to be what? 216. 216 x squared. 4 times 2 is 8. 3 times 3 times 3 is 27. 8 times 27. Is that 216 also, I believe? I believe it is. 216x. 3 to the 4th power is 81. And we're done. That would be the expansion. That's the expansion of that binomial, 2x plus 3 to the 4th power. See how we use the binomial theorem to generate that expansion? Any questions about that expansion there? All right, let's try another one. Let's see if we can expand 3 x squared minus 5y to the 3rd power. Let's see if we can expand this out here. Using the binomial theorem. First, the leading coefficient is going to be 3 choose 0 times the first term, which is 3x squared raised to the power of the binomial, times the second term, which is negative 5y raised to the 0th power. Plus, the second term's leading coefficient would be 3 choose 1 times the first term, 3x squared, power decreased by 1 down to the second power. The second term's power increased by 1 to the first power. Next term's coefficient would be 3 choose 2 times the first term's power, 3x squared, reduced down to the first power, and the second term's power increased by 1 up to the second power. Finally, the last term is going to be 3 choose 3 for the coefficient times 3x squared to the 0th power times negative 5y to the 3rd power. Essentially, that's your expansion. Now we just need to clean these things up and evaluate these things. 3 choose 0 is going to be what? 1. 3x squared cubed. 3 cubed is 27, and x squared cubed is x to the 6. So this is going to be 1 times 27 x to the 6 times 1. So this is times 27 x to the 6th. 3 choose 1 is going to be 3 times 3 squared is 9 times negative 5. 9 times negative 5 is negative 45. X is raised to the second power and squared. X squared squared is x to the 4th power. 3 choose 2 is 3. 3x squared to the first power is 3x squared. Negative 5y to the second power is going to be 25y squared. So what's 3 times 25? 3 times 25 is 75. And we got x squared, y squared. Hold on a second. Let me double check something here. Oh, this term here should have a y to the first power here. Wait a minute here. Yeah, there would be a y to the first power here. And this term is 3. This is 75 x squared, y squared. Okay. 3 choose 3 is 1. 1 times 3x squared to the 0th power is 1 times 1, which is 1. And negative 5y cubed is negative 125y cubed. All right, anyways, cleaning this up, we got 27x to the 6th. 3 times negative 45 is going to be negative 135 x to the 4th y. 3 times 75 is going to be 225 x squared y squared. And then we're going to have negative 125 y cubed. Okay, that would be the expansion, or the expansion of 3x squared minus 5y to the third power. Now, you're probably wondering, wait a minute, I thought all the powers of the terms has to be equal to the power you're raising the binomial to. How come 6 is not 3 here? How come 4 plus 1 is not 3? How come 2 plus 2 is not 3? Well, the reason why is because our terms have variables raised to different powers other than 1. But you can see this is evident right here before we, went further in raising these terms to powers. First, 1 plus 2 is the third power. 0 plus 3 is the third power. 3 plus 0 is third power. 2 plus 1 is a third power. All right. Any questions about that expansion there? So you don't really need Pascal's triangle anymore because these combinations are going to generate your coefficients, which may have to be multiplied by other numbers based on the coefficients of the individual terms. All right, classwork number 2. Let's see if you can expand this out using the binomial theorem. 2t to the fourth power minus 3v to the third power. Expand that out by using the binomial theorem. Okay, we'll call that classwork number 2. All right, so when you use the binomial theorem and expand this thing out here, your coefficients are 3 choose 0, 3 choose 1, 3 choose 2, 3, 3, 3, 3 choose 3. Your first term's raised to the third power, then its power decreases by 1 each subsequent term. Second term of the binomial starts at the 0th power and its power increases by 1 subsequent terms. Now it's a matter of cleaning all this up. 3 choose 0 is 1 times 2 to the third power. T to the fourth cubed is t to the 12th power. This is all 1. 3 choose 1 is 3. 2 to the second power times -3. T to the fourth squared is t to the 8th. B. 3 choose 2 is 3. 2t to the fourth to the first is 2t to the fourth. -3v squared is 9v squared. 3 choose 3 is 1. This is all just 1. And this is -3 to the third power times v cubed. This is going to be 8t to the 12th. 3 times 4 is 12 times -3 is -36. T to the 8th v. 3 times 2 is 6 times 9 is 54. T to the fourth v squared. And -3 cubed is -27v cubed. Did anybody get this here for that expansion? Yeah. Anybody get that? Did anybody not get that? All right, I'll assume we all got it. Okay. Now we're going to develop a formula that will give us a specific term of an expansion instead of writing the whole expansion out. To do that, we need to observe this pattern. N choose 0. If we're raising a binomial to the nth power, the first term starts off the nth power, the second term starts off at the 0th power. Plus the next coefficient is n choose 1. First term's power decreases by 1, the second term's power increases by 1. Plus the next exponent is n choose 2. First term's power decreases by 1 again, which means it has decreased by 2. Second term's power increases by 1, or has increased totally by 2. Plus n choose 3. First term's power is n minus 3. Second term's power is up to the third power. All right. Notice this is term 1, term 2, term 3, and term 4. I want to draw your attention to some things here. Notice R always starts out at 0. Even though we call this the first term of our expansion, R starts out at the 0th term. In fact, R's value lags 1 behind the term. 1 behind the term. Okay. Notice N is subtracting off what R is in each term. N minus 0, N minus 0. N minus 1. N minus 2. N minus 3. Notice the power on B lags 1 behind the term. 0 compared to 1. 1 compared to 2. 2 compared to 3. 3 compared to 4. So there's how we can develop this very important little formula to find the kth term of a binomial expansion. Let n and k be positive integers. With k being less than or equal to n plus 1. Then the kth term of the binomial expansion, a plus b to the nth power, the kth term is going to be given to us by this formula. N choose k minus 1 times a, the first term raised to the n minus r power, times b raised to the b being raised to the same power that r is. And there you go, ladies and gentlemen. This will generate the kth term of a binomial expansion. Notice when the binomial is raised to the nth power, we start with n here for the combination, n here. All right. And to find the kth term, r starts out at the k minus 1 power. And the power on the first term is n minus k minus 1. Power on the second term of the binomial is k minus 1. This is a very useful formula which can help you very quickly find a specific term of a binomial expansion without having to go through and write out all the terms of the expansion, which, granted, with the binomial theorem is really not that bad, but still it is time consuming. Okay. See if we can put that to work here to do problems that you'll be confronted with Alex. Suppose I want to find the eighth term of the binomial expansion 2x plus y to the 4th power raised to the 10th power. I want to find just the 8th term of this expansion. I don't want the whole expansion. Well, first of all, we need to understand that n is the power the binomial is raised to. N is 10. K is 8 because we want to find the 8th term. Our first term of our binomial is 2x. That's our A term, if you will. Our B term of our binomial is our second term of our binomial, which is y to the 4th. Ladies and gentlemen, all we got to do is feed things into this formula and we'll crank out the 8th term of this expansion. And you got to admit, to expand this all out, even using the binomial theorem, would take quite a while because we're raising this darn thing to the 10th power. And don't try to actually multiply this by itself 10 times. You'll be basically working on this for about a week or two. All right, so here we go. So the 8th term, we follow along, is going to be what? N choose k minus 1. N is 10. 10 choose k is 8. 10 choose 8 minus 1. Times the first term is 2x. Raised to the n minus k minus 1 power. N is 10. Minus k minus 1 is 8 minus 1. Times the second term is y to the 4th. Raised to the k minus 1 power, which is to say 8 minus 1 power. And there you go. That's going to be your 8th term. So we're really going to have 10 choose 7 times 2x raised to the, what's this, 10 minus 7 power? 10 minus 7 is 3. 8 minus 1 is 7. Y to the 4th to the 7th power. Get on your calculator. What's 10 choose 7? 10 in combination with 7. What does that give us? 10 choose 7 gives us a coefficient of 120. This is 2 to the 3rd power. 2 cubed times 8 cubed times y to the 4th power raised to the 7th power is y to the 28th power. Ladies and gentlemen, this is 8 times 120. Here's your 8th term of this expansion. It's 960 x cubed y to the 28th. Done. That is your 8th term of that binomial expansion, of raising that binomial to the 10th power. That would be the 8th term of the expansion. And we're done. Any questions how we used that formula we developed?
Ladies and gentlemen, to find the 8th term of this binomial expansion. That's a lot quicker than if you were to try to multiply this out by itself 10 times. Or even use the binomial theorem. It would still take a long time to find the 8th term. This formula is a pretty powerful little formula, what it can tell you. Any questions how we found that term there? All right. I have a question for you, ladies. How many terms is this expansion going to have? How many terms will this expansion have? Well, notice the number of terms always what is one more than the power the binomial is raised to. So how many terms are we going to have for this expansion?
11.
There would be 11 terms, correct? I found the 8th term. All right. Now, here's what I want you to do. I want you to use this formula, same binomial expansion, and I want you guys to find the 6th term. The 6th term of this binomial expansion using this formula. We'll call this classwork 3. Find the 6th term using this formula for this binomial expansion. I found the 8th term. I showed you how to do it. You guys find the 6th term. All right, go ahead. You find the 6th term of that expansion. Done the same way as I found the 8th term. Just the numbers are different. All right, to find the sixth term, you let k be 6. N is 10, A, the first term is 2x, second term is y to the fourth. Drop things into the formula. Go through and crank things out. And you get the sixth term. Did anybody get that term?
Yeah.
All right.
Yeah.
It is working out, this formula, making sense? They can save you tons and tons of work. Okay, good. All right, that's one typical question that you'll be asked using Alex, okay? I'll give you a binomial expansion, maybe a binomial raised to very large power, and I'll ask you to find a specific term. Instead of going through the entire expansion to find that specific term, you might want to make use of that formula to save a lot of time, okay? All right, that's a typical problem. Here comes another typical problem. Another problem says this: find the term containing a to the 9th power for the binomial expansion a cubed plus 4b to the 6th power. So that's what we want to do. We want to find a term that contains a to the 9th power for this expansion. I just want one term, the term that contains a to the 9th power. I don't want the complete expansion of this, okay? All right, so here's what we're going to do now. We're going to use our formula and choose k minus 1 times a raised to the n minus k minus 1 power times the second term b raised to the k minus 1 power. Now, our first term, notice, our first term of our binomial is a cubed. Our second term, which I'm generically calling b, okay, is 4b. My first term, generically I call it a, is a cubed in this case. My second term is 4b. What's n? N is the power the binomial is being raised to, which is the 6th power. Okay. So notice, ladies and gentlemen, I don't care about, I just want to find a term that has a to the 9th power in it, correct? So the only thing that concerns me is that my a raised to this power has to be a to the 9th power. Being the case, I'm going to extract this factor of my formula, and I'm going to force this factor to be equal to a to the 9th power. Do you see that there? Now we fit in what we know. N is what? 6 minus k. We don't know k. We don't know what term has a to the 9th power. So we leave k as k. But we set this equal to a to the 9th. Now we're going to equate the exponents. So therefore, this 6 minus k minus 1 has got to be equal to 9. And now all we have to do is solve for k to determine what term has a to the 9th in it. So we solve for k. So distributing the negative sign in here, we got 6 minus k plus 1 equals 9. This is 7, subtracting 7 from both sides, we get 2, dividing by -1. K walks out with a value of negative, wait a minute. Make sure I did this right here. 7. What is going on here? Oh, my bad. What's my first term? What's my first term of this binomial? It's not just a, it's what? It's a cubed. Okay, so we got to back up. Yes, I want to set my first term raised to this power equal to a to the 9th, but I did not replace a with what the first term is. The first term is a cubed for this binomial. So what I should have done here is I should put a cubed in for my first term a, and then that's raised to the n minus k minus 1 power. That's got to be equal to the a to the 9th power. There we go. Sorry about that. So we really have a to the 3rd power raised to the n is 6 minus k. We don't know k, so that's k minus 1. That's got to be equal to a to the 9th. We're now going to set this exponent equal to this exponent. We can do that because we have equivalence between like bases. So 3 times quantity 6 minus quantity k minus 1 has got to be equal to 9. Now we solve for k. All right, so we got 3 times, this is going to be 6 minus k plus 1 after distributing the negative sign in here. So we have 3 times 6 plus 1 is 7 minus k equals 9. 21 minus 3k equals 9. Now we just solve the simple first degree equation for k. And when you get done solving this for k, you discover that k is equal to 4 rather. So we're talking about the 4th term here. So it's the 4th term that has a to the 9th in it. All right, the 4th term. And we're done. I just wanted to know what term it was, and it is the 4th term of this binomial expansion that does have a to the 9th in it. The answer is the 4th term there. Any questions how we determine what term that was? It's the 4th term. Yeah, don't forget to replace this generic a with what the first term of your binomial is, okay? Or if you want to find what term has b to some power, you got to replace the generic term b with what the second term is. 4b would have to go in 4b. Just don't forget to do that. Okay. That's another very typical problem that you could potentially run into there. All right. All right, now, suppose you actually wanted to find the what the 4th term is. I mean, I just wanted us to find what term had a to the 9th in it, a to the 9th in it, and that is the 4th term. But how would we actually determine what the 4th term is? Well, now we know that it's the 4th term. We can use this to generate the actual 4th term of this expansion. So the actual 4th term would be 6 choose 4 minus 1. Remember, k is 4 now. So 6 choose 4 minus 1 times the first term, which is a cubed, raised to the 6 minus 4 minus 1 power, times the second term, which is 4b, raised to the k minus 1 power, k being 4. So this is going to be 6 choose 3 times a to the 3rd power raised to the, this is going to be 6 minus 3 or 3rd power times 4b raised to the 3rd power. Now we want to try to obviously, we want to simplify this here. So this is going to be your 4th term where k is 4 and n is 6. Okay. First term of which is a cubed, second term of the binomial is 4b. Now what's 6 choose 3? Or 6 in combination with 3? That's going to give you 20. So this is going to be 20 here. So 20 times a cubed is a to the 9th power. There's your a to the 9th power. See that? Everybody see how the 4th term does generate a term that has a to the 9th in it? You can see it. 4b cubed is 4 cubed. 4 times 4 is 16 times 4 is 64. B cubed. Finally, 20 times 64 gives you 1280. So this would actually be the 4th term of that binomial expansion. And notice, yes, the fourth term does have the desired factor of a to the ninth in it. So it makes sense that that would be the fourth term. Is this making any sense? What's going on here? And make sure, of course, that you do look at the examples in your section, which will help to re-emphasize this material in your mind and help you to sit more confidently into your thinking. All right. So that's a typical problem that you could be concerned with. Another one. And here's another typical problem you could be confronted with while using Alex. The problem comes at us like this. Find the middle term of the binomial expansion, k cubed minus 1 raised to the 10th power. Find the middle term of this expansion. Now, ladies and gentlemen, we don't actually want to go through and expand this all the way out. That would be very time consuming. And in fact, how many terms would this expansion have since we're raising this to the 10th power? How many terms would it have in its entire expansion?
11.
It would have 11 terms. And I'm not asking you to give me all 11 terms. I don't want that. All I want is for you to find the middle term of this 11-term expansion. All right, now how are we going to do that? Well, we know there's 11 terms. There are 11 terms in this expansion. So the question is, what is the middle term? You know, if you got 11 terms here, look at here's term 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What's the middle term? Well, you agree that might be, I think that's going to be what, the sixth term, right? Where you got 5 on the left and 5 on the right. 1, 2, 3, 4, 5, 6. This would be the middle term. The middle term, ladies and gentlemen, is really the sixth term. Isn't that true? 5 on the left, 5 on the right. That's the middle term. So we really need to find the sixth term of this expansion. That's really what's going on here. So to find the sixth term of this expansion, we are going to use, you guessed it, our formula we developed. And this is the formula that will enable us to crank out the sixth term of this expansion, which is a heck of a lot quicker than if we were to actually expand that all out. So now, what would n be for this formula here? I want to find the sixth term. So my n is going to be what? My n is what? The power the binomial is raised to. My n is going to be 10. K is equal to the kth term I want to find. Well, I want to find the sixth term. So k has to be 6. That is the middle term. Generically, my first term of my binomial, which I call a, just keeping with your textbook, a is really k cubed. That is the first term of my binomial. But generically, I've been calling my second term b. Well, b is the second term, which is really -1. All right. I think we're ready to put things into the formula and crank out the sixth term or the middle term of this 11-term binomial expansion. So here we go. So we got n in combination with k minus 1. So we got 10 in combination with 6 minus 1 times my first term, a. But a is what? K cubed. So k cubed raised to the n minus k minus 1 power. So k cubed raised to the 6, raised to the 10, minus 6 minus 1 power, times b, the second term of my binomial, in this case is -1. So that's -1 raised to the k minus 1 power. So -1 raised to the 6 minus 1 power. And there you go. That would be the middle term of this binomial expansion. And of course, I would like you to go further and actually, simplify this. Don't leave it looking like this. So we got 10 in combination with 5. Now this is going to be k cubed raised to the 10 minus 6 minus 1 power is 10 minus 5 power of 5th power. Negative 1 to this is going to be negative 1 to the 5th power. And I need to know what 10 choose 5 is. So you go to your calculator, use your combination function. 10 choose 5 gives me 252. Now you could also get to 252 by going all the way down to the 10th or the 11th or 12th row of your Pascal's triangle. But later on, it's so much simpler just to compute that combination. Now, k to the 3rd power to the 5th power is k to the 3 times 5 power, k to the 15th power. Negative 1 raised to an odd power is negative 1. So this is negative 1. Here's your answer. Negative 252 k to the 15th power. And ladies and gentlemen, we are done. This would be the middle term of that 11-term binomial expansion. That's your middle term. So again, you have to marvel at this formula and the amount of time it's saving you. And if you don't believe me how much time it's saving you, you go right ahead and multiply this by itself 10 times, and you'll start to realize what a marvelous formula this really is. Okay. It saves you tons and tons of time. Okay. All right. What is it? 159. All right. Classwork number 4. Any questions about this problem here? We found the middle term of that binomial expansion. Classwork number 4. I want you to find the term containing p to the 12th power in the binomial expansion, p to the 4th plus 3q raised to the 8th power. I want you to not only determine what term yields, the factor of p to the 12th power, but I actually want you to find the actual term. All right, you go ahead and do that. We'll call that classwork number 4. I demonstrated how to do one of these. Just go back in your notes. You're going to walk down the same path. Okay. Okay, so. Notice n is equal to 8. Our first term is p to the 4th, and our second term in our binomial is 3q. We want to find the term that contains p to the 12th power as a factor. So that being the case, I am interested in this factor being equal to p to the 12th, p to the 4th raised to the 8 minus k minus 1 power. So I set 4 times 8 minus k minus 1 to the 12th power. Then I solve for k, and I get k is equal to 6. So it is the 6th term. Now to actually find the 6th term, knowing that n is 8 and k is 6, first term is this, second term is this. All we got to do is put things into our formula. So we put things in our formula here, and we can actually crank out the 6th term. And when you're done, you do get, for the coefficient, large coefficient, 13,608 times p to the 12th, q to the 5th. And did anybody persevere to the end and get that?
Yeah.
All right, so we did get that there. All right. So I've shown you some typical problems that you will be asked on Alex, whether it be the homework quiz or the exam, or even the final exam for that matter, that pertain to the use of the binomial theorem or this formula that we have developed to find a specific term of a binomial expansion. And so, ladies and gentlemen, I have shown you everything that I need to show you out of this last section, 8.5. And because of that, that brings to an end the lecture portion of this course. Again,
Move it down one more time, please.
like this.
Yes, thank you.
All right. So again, some reminders.